Yes, good morning, students. I hope everyone is fine. I know people are not fine. The last time we were together, the lecture was a bit very uncomfortable to most of us. And I've decided now to use another approach. Now, remember we are looking at some theorems, and the first theorem that we are looking at was the fundamental theorem for gradient. Now, we say that for gradients, our first theorem is, remember, gradient is a change in temperature. A gradient, if you have a scalar function, t, whatever scalar function, when you take the change in this one is what we call a gradient. They change the slope and so on. Now, the first theorem tells us that the sum of the changes in temperature along a given path from A to B. I beg your pardon, what I'm saying, the sum of the changes in temperature along a given path, the L, from a particular point A to a particular point B, can always be given just by taking the value of the temperature at B, take away the value of temperature or the value of that function at a point A. And now A and B, remember, these are your limits. In mathematics, I call them limits, but here you can refer to them as boundaries. All right, this is the upper and this is the what? This, you can call this one the upper, and this one is the what? The lower, right? So what we are saying is that the sum of the changes of a given function t, for example, I told you temperature along a given path, the L or L from A to B, can be defined as the value of the function at B, take away the value of the same function at a point what? At a point A. And I told you that if you have your function like that, suppose that is our function, and assume this is a point A and this is a point B, they have their corresponding values of f of B, f of what? F of A. This is now mathematics. So this, the left hand side is represented by, because the sum from A to B, you divide them into small segments that we call the L, and when you sum them from here to here, they will give you also the total change in the function t, and in this case we are taking t to be our temperature. All right, or you can just deal with the upper limit and the lower what? And the lower limit, and the difference will still give you the same answer. So that is why we are saying that okay, before we go on, and the other point that I want you to understand is that it was discovered that since when you sum from A to B is the same as taking the upper limit, subtract it from the lower limit, this one proved to us that now the path you have taken does not matter, but what matters is the starting point and the end what? So even if you decide to move like this and come back to A, the path you have taken does not matter. What matters is the starting point and the end what? Because the two are what? Are equal. If the two are not equal, then the path would matter. But since I can get the same answer when I'm just using the starting point and the end point, then the path you have chosen does not matter. Even if you move like this and come back there, it is still, you'll get the same point, as long as this is the starting point and that is the end point. But the unique thing, if you move like this and come back like that, in other words, if A, you move from A and come back to A, the change in temperature because the point is still the same, the sum of the change in temperature along that path you have taken, A to A, would be 0. Okay, and anything that behaves like this, you shall see later that this one also refers, this one means that you have moved in a closed path. All right, and sometimes we write this integral, you can decide to write it like, if you don't want to write it like this, now we are going to write it now like this. This is in a closed what? That one refers to a closed path. All right, this can be so mathematical, but now in our subject, in our continuity, we are going to be taking like that. So if it is equal to 0, by the factor I have seen this, that one means closed what? Closed path. As long as you say an integral with a sign, with a circle, that means it is what? A closed what? A closed path. Now, let us assume that our temperature, which depends on x, y, and what? Z, is defined as x, y squared product. And maybe we want to see the sum, we want to get the sum of the change in temperature from the origin 0, 0 to 0.210. So ideally what this one means that you are going to take the sum from A to point B, where A is the origin and B is 210. You want to see the sum of the change in temperature along this path, the L which starts, but we are interested from A to what? To B. But instead of calculating this one, now we know we can get it as this one by looking at the upper limit. We subtract it from the lower what? So this one implies that our upper limit is 210. Remember, this is your x, this is your y, and that is your z. So if you substitute it in our function, the function tells you get x, multiply it with the square of what? X is 2, multiply it with the square of y, which is 1. This one gives you 2. So now when you look at 0, 0, 0, now this one, when you put it, that means x is 0, y is 0, so everything is 0. And when you subtract 2 minus 0, this one gives you what? 2. So that is what we are saying. So that now tells you that the sum of the change in temperature from a point A to a point B, from here to here, the change in temperature, the sum of the change in temperature is just what? 2. But these are small changes that we have been summing from here to here. They're just emphasizing to you that they're what? They are 2. Or you can decide to follow the path. You can decide to draw that this one started from 0, x went to a point 2, then you discover that this one is already in the xy plane alone. So from there you moved one step in the y. So that is how we moved. Assume that this is 1. So he never moved any distance in y. So here, even if I have my what, assume this is my z. He never moved in the z, but only moved to the origin was here, 0, 0, but he moved like that. So if you want to compute now, if I'm to deal with the left hand side, if t is defined as xy, then the change in t, you differentiate x. When you differentiate x, you remain with y squared in the I direction plus 2xy in the j direction. All right. I hope you know when we talk of dt, you remember it is dt, the x in the I plus dt, dy in the j plus dt, dz in the what? in the case. So I'm just differentiating this function with respect to x to get this component. I differentiate the same function with respect to y to get that component. Z is not there, everything goes to 0, that's why it is not there. So if you know that the x is that, so the second thing you'll ask is the L. The L is just the linear combination of the small changes in all the unit directions, the Z. Okay, so now if I'm to follow, this is step 1, you move x moved from 0 to 2, I'll call this one 1, and step 2 we moved in the y 1 step. Okay, that is step 1, that is step 2. So along the first path, x moved from 0 to 2, y was constant, so that implies the change in y is 0, the change in z is what? Is 0. What does this one imply? That when you are going to dot, when you dot this one, all right, all the y's are 0 and the z's are 0, so you only remain with the x component. So you'll be dotting this one with that one, which gives you y squared dx. But y is 0, so the whole thing comes to 0. So the integral of this one along the first path from 0 to 2 will give you 0. This is the change in t. This one will give you what? Will give you 0, because the whole of this one, we have seen it is what? We have seen it is 0. It gives us what? It gives us 0. So this one is a longer method, but just to prove to you that both sides are what? Are the same. They are equal. So if you are going to use the second root, that means in the second root, what does that mean? It means that x will be 2 and y shifted from 0 to what? To 1. So that means the x is the same as the z, and all this one will be 0. So you will see that your dt, when you dot it with the L, remember these two components now zeros, the z and the what? And the x, so you only be remaining with the y. The y is the one that you are going to dot it with the y, with this component of what? Of dt, the change in t. And this one will be giving you 2x y the what? Dy. But x is what? X is 2, so this one gives you 4. This one will give you 4y dy. And remember, y is changing from 0 to what? To 1. And when you integrate this one, all of us, we can integrate it. It will give you 2y. And we're integrating from 0 to 1, so the answer becomes 2. So you see, both ways, we shall still get the same answer. But in practice, for us, you will not be able to use this. What you need to know is just to use the upper limit, take away the lower limit. So what this one helps us is that if it helps us to sum up all those small changes along a given what? Along a given path. And if we see that the sum of all those small changes along a given path is 0, all right, what does that one tell us? If you see that the small changes, all of them add up to 0, then that means you are dealing with the closed what? The closed loop, and the starting point is the same as the end what? The same as the end point. So what I want you to take home is that you only just need to know this fact that should stick in your what? It should stick in your head. This one is the most important fact that we need to stick in our heads. I thank you.